Esters and esterification. Reaction of an alcohol with an acid when subjected to heat and in the presence of sulfuric acid forms an ester and water. The process of doing so is esterification. Sulfuric acid works as a catalyst which increases the speed of reaction. However, the water molecule produced in that reaction is absorbed by sulfuric acid. Now we all know that when sulfuric acid touches water, it produces heat. It's an exothermic reaction. This thereby automatically increases the heat of that reaction. This also in its own way prevents the reverse reaction from taking place, thereby increasing product yield. When naming an ester, there are certain ways to go about doing this. Let us take, for example, ethanol and react it with ethanoic acid. The ANOL portion of the alcohol will become a YL, and the OIC portion of the organic acid will become an OATE. Hence, in the esterification of ethanol and ethanoic acid, it will produce ethyl ethanoate plus water. Let us work out an example using ethanol and ethanoic acid. So that's ethanol. Let's make up ethanoic acid. So when this reacts with sulfuric acid and you heat this up to about 70 degrees, esterification will take place and it will result in this. So it's going to happen is the OH from here will react with the hydrogen and it will combine with the hydrogen from the hydroxyl, and let's remove that. And it's going to form ethyl ethanoate. So we're going to put here and we're going to release water. So this is going to be called ethanol. That is ethanoic acid. It's going to give us ethyl ethanoate and water. This is going to be the reaction which takes place. Let us go into another substance, and for that we're going to use mole view. So I'm going to close this. I'm going to change this default structure, and if you're going to say, for example, use ethanol, so it's got 2 carbons, so I'm going to put 2 carbons, and if you click on this it will give you the primary structure of two carbons, which will become an ethane. So it's CH3, CH2, and let us make this an O. And then we add a hydrogen there. So this is ethanol, CH3CH2OH. Let us add react it with butyric acid. So let's see what's going to happen. Butyric means 4 carbons. So I'm going to select 4 carbons. 1, 2, 3, 4. Now let's also ensure that all the carbons are satisfied. So CH3, CH2, CH2, C, and then butyric acid means C double bond OOH. So I'm going to convert this to a double bond, and I'm going to put an OH O over there, and this will become an O, and a H, and this portion will disappear. The good feature of using mole view also helps you to clean up structures. So let's clean up the structure. So this has become our ethanol, and that is your butyric acid. So I'm going to move this up closer. So not to get confused, there are two different molecules. The OH is the ethanol. The 4 carbons, 1, 2, 3, 4, means it's butanoic acid. So that's what it is. The CH3, C3, and then the 4th carbon has a C double bond OOH. In the reaction of esterification, the OH of the acid will react or will combine with the hydrogen of the alcohol to form water, and the new structure on combination will be like this. So you're going to put in so it has a CH3, that is your 2nd carbon, and we are going to react. This was the this will become the O, a single bond here, then a double bond here, just to keep it in. Then we're going to add the other 3 remaining carbons. 1, 2, 3, and all we do is then click on that, and so we have your ethyl butonate. So that's what the name is going to be, and I'm going to clean up this structure. So I'm going to first select it. and I'm going to clean it up. There we go. CH3, CH2, CH2, C double bond O with an O, and then that is your alcohol. So this portion over here is the acid portion. Remember, anything with the double bond and the carbon links is the acid portion, combining with the alcohol portion. So this is going to be ethyl because it's got 2 carbons, and then you have 4 carbons there, so that will become a butanoate, butanoate, butanoate. You can try out different structures and try to see if you're able to do so. You can now convert this if you want from a 2D to 3D image, and you can see your structures over here. So that's the ester, kind of a grape, a fruity smell which will occur. Remember, butyric acid has got a unpleasant odor, and you've converted this to a fruity odor. That's the objective of esterification. The other one is, of course, if you want to send the structure, you could, and it will send it. You can save it as a PNG file, and it will look like this. So this could be then sent to your instructor for evaluation. Thank you. Let's do another esterification structure. In this case, I am going to use a benzene structure. I hope you will be able to identify what I'm going to be drawing. So let's go along, and please pause the video and see if you can figure out what's happening. This is my, not that one, this is my benzene structure. To the benzene structure, I am going to convert it to first a benzoic acid, and in that I'm going to do this is benzoic acid. To this, I'm adding a hydroxyl group to it. What is this structure's name? Hydroxybenzoic acid. This is also called as salicylic acid, the C double bond OOH. Now, if I add a methanol to have a CH3 and you have an OH group over here. Can anyone let me know, if you heat this up with sulfuric acid and at 70 degrees, what is going to happen? Will release water, and so now you're going to get what is called as methyl, because this was the methanol, salicylate. So let's draw that structure. This was your salicylic acid, and to that we had so this structure. This was your alcohol component, the CH3 with the O. The C double bond O was your acidic component, which was salicylic acid. That will become, the IC will become salicylate, and the methanol will now turn into methyl. So this product over here will be called as methyl. The alcohol component always is named first. So methyl salicylate is what is formed. Just to let you know, this is the smell of wintergreen, and it is the active ingredient in any muscle relaxant lotions or ointments. Hey guys, this is the esterification portion once again, and I hope that at the end of this video you will get an understanding into not only esterification but a little more deep depth of the chemistry which is involved in organic chemistry. So here goes. So I'm going to start off this one by making up a very simple structure for you, and it goes like this. You can see that we have 3 carbons. So let's try something. So let's have a look at what is going to be. In this process, I think it would be fun if you could try to guess and see where I'm going with. So we have 3 carbons. We have alcohol groups, or hydroxyl groups rather, and this becomes what is called as, for those who got it good for you, otherwise it's still, at least you attempted, it's also called as glycerol. So glycerol has got it's got 3 hydroxyl groups attached to the carbon chain, and if I react this with you can see that it is a C double bond OOH, so it has to be some form of a acid. So you have seen that this is an acid, this is an alcohol. We do we know what is going to be formed over here? Well, you were right if you guessed it is going to be an ester, and that would be great if you got that right. So, and these are different types of acids, and they're called as fatty acids. Why? Because the R1, R2, R3, they are different types of long chain fatty acids. So they are long chain carbon groups, uh, which may or may not have double bonds. Could be single bonds, it could be double bonds. Some R groups even go to chain lengths of 20, 22 carbons. So in this is like an abbreviation. So we really cannot identify what the fatty acid is here, but it is called as a fatty acid. So if I take a fatty acid and I mix it up with an alcohol, it is going to give me an ester. Just to give you another piece of information, this exactly is oils. Anything edible oils that we eat, for example, olive oil, um, palm olive oil, sunflower oil, soybean oil, these all have very much this very same structure. It's got a fatty acid and it is interacting with an alcohol. Let's have a look at remember these three guys. These are the water which is going to go out from each one. And this is what's going to happen. I'm just going to first draw the structure, the backbone of the three carbons. and I'm going to first ensure that we got that portion correct. So this what we see here is our oil, and hence of course we're releasing over here plus 3 water molecules. So this is when fatty acids mix with glycerol to form what is called as an oil and water. Now, as you can imagine, this fatty acid, this glycerol is a large molecule, extra large. And I'm just giving you another insight into things. If I remove this large molecule, if this large molecule in fact in an oil, which is the alcohol component of the oil, it is present in every oil. The glycerol molecule is present in every edible oil. It is the fatty acids which keep changing, which gives us different flavors of that oil. Now, why can't I use this oil in my car? Well, it won't burn because it won't ignite. But that is due to the fact that this glycerol molecule is a large, heavy molecule. It needs a lot of temperature for any form of an auto or a self-ignition to take place. What if I take out this large molecule from here and put in a methanol? So if I put in one methanol here, one methanol here, one methanol here, I will get what is called as a methylated fatty acid, and that itself is what is called as biodiesel. That is what we use, that's how we convert an oil, a regular eating oil, what is edible. I remove this large glycerol molecule and substitute it with methanol, and that whole process is what is also called as derivatization. So if I remove this large blob of a molecule of glycerol and I add a methanol, which is a very small molecule, as you can even see by the size of it, and it becomes a far more volatile compound, and hence it becomes easier to use in automobiles and so on and so forth. So this is just an insight to what I wanted to show you.